Welcome to our discussion on polynomials. First of all, you need to know what a polynomial is. And basically in algebra, we are always dealing with variables. And what we're going to look at now is kind of a very basic, very common type of thing that you'll see in algebra. Okay, so let's look at some vocabulary. A polynomial is made up of poly, meaning many terms, right? If you have a polynomial with one term, it has a special name. We call it a monomial, mono meaning one, right? If it has two terms, binomial, bi meaning two, just like bicycle, right? And three terms is a trinomial, tri like a tricycle. And then the rest are just called polynomials. And in fact, of course, monomials, binomials, and trinomials are just specialized versions of polynomials. So these are all polynomials. We just gave these three a special name. Now, what is a term? A term is anything that is separated by pluses and minuses. Okay, so a term is any clump of things that are stuck together over multiplication, like 10x. But 10 plus x is not, because those things are brought together over addition. If it was 10x squared, that's still one term. If it was 10xy, that would still be one term, because those things are all stuck together. Even if it was 10x over y, divided by y is still a form of multiplication, because you could turn that into 10x times y to the negative 1, right? So all of those are still just basic terms. The degree of a term is basically the sum of all of the powers. So 3 to the x is a first degree term because the power of x is only 1. 5xy is a 2 degree or a second degree because there's a 1 degree for the x, a 1 degree for the y, so it has a total of two powers, right? 2 degrees. 2x squared is also second degree, and if we look at 9x squared y cubed, that's a fifth degree because you have 2 of the x's and 3 of the y's. You're basically counting up how many variables you have, but be careful, because if one of these was on the bottom and it became a negative, then that takes away from the degree. Okay, the degree of a polynomial is just the largest degree of any of the terms. So when you look at a polynomial, find the term that has the highest degree. Whatever that degree is, that ends up being the degree of the polynomial. Normally we write polynomials from highest degree down to lowest degree. So you'll write the term with the highest degree first, and then the next highest, and so on and so forth. So you get all the way down to the constant term if you have it, right? And the constant term has degree of 0 because the number 5, if that was a term, it technically is 5 times x to the 0 because x to the 0 is just 1, right? So it's degree of 0. All right, some more terminology. A first degree term is called a linear term. So 3x here, that's a linear term because it's only got a degree of 1. And that makes sense because a linear function is a line, and we know linear functions are y equals mx plus b, and mx has degree 1, right? So a straight line is a polynomial of degree 1. A quadratic is a special name we give to polynomials that are of second degree. And you've seen quadratics before. They're very popular. They're very common. We see them all the time in algebra and many other subjects. But you'll know kind of the basic format: ax squared plus bx plus c. There's your basic quadratic. The numerical part of a term, so in this case a, right, whatever number that is, that's called the coefficient, and b here would also be called a coefficient. So if 3x was my term, 3 would be my coefficient, right? 5xy, 5 is the coefficient, so on and so forth. And nothing earth-shattering there. All right, let's look at some examples. Can we classify each of these? So can we all see that a is a monomial of degree 1? B is a trinomial because it has 3 pieces of degree 2 because that's the highest power. What about C? What kind of polynomial is that? Well, hopefully you're all saying it's a binomial. Yep, because it's got 2 pieces. And what is its degree? Degree 3. All right, what about this one? Again, a binomial. And what's its degree? Degree 5, right? Because this is degree 3, this is degree 5, that's the highest. Okay, now what about this last one? What would we say that? I mean, that's technically a polynomial of 0 degree, but it's really just a constant function, right? You can think of it as a monomial with a 0 degree, but we would normally give it the term and just call it a constant function. So a lot of things can be stuck under the umbrella of polynomials, but specialized ones normally get special names like quadratics and constant functions and things like that. Okay, like I said before, we always want to, if we can, write our polynomials in highest to lowest degree form for the terms. And that helps to make sure that your polynomial looks like mine. And it's just easier to check to make sure we get the same answer, so to speak. All right, when we're working with polynomials, we definitely need to simplify them because otherwise they can get very unwieldy and very ugly. And really all you can do when simplifying polynomials is to combine like terms, or what we call similar terms, and then use the distributive property to kind of get rid of parentheses, and then again sweep up similar or like terms. And that's about all you can do with a polynomial if you're just trying to simplify it. Now obviously if you're trying to solve for a polynomial, there's much more you can do. But if you're just simplifying it, that's all we can do. So to put a polynomial in its simplest form, you want to write it with all of the terms written out from highest degree down to lowest degree. And if there are two terms with the same degree, you arrange them alphabetically, right? So like if you have a 3x squared and a 5y squared, you would put the 3x squared first and the 5y squared second. And again, that's just so your polynomial looks like mine. Okay, so some would argue that this is already simplified. And really, for most instances, it's going to be better to leave your polynomials factored. Because if we're going to solve these things and we have to like set them equal to 0, well, they need to be factored to solve. So it's usually not a good idea to multiply these things out and put like terms together and all that kind of stuff, unless we specifically need to do that for some other reason. For now, we're just doing it for practice, but in a normal application sense, it's much better to leave things factored because that's how you can solve them. Okay, if it's something simple like A, you just use the basic distributive property, which basically just means you take 3x and multiply it by each term. So 3x times x squared, and then 3x times minus 1. When you get something like this, you might remember foiling first, outside, inside, last. But then when you get to something like this, you can't do FOIL anymore because it's a 2 and a 3. That's why I tell my students, don't learn to FOIL. FOIL only works when you have a 2 and a 2. Instead, just learn to always be systematic. If I'm going to multiply this thing, I'm going to start with my first term and I'm going to distribute it through. So I'm going to go 2x times x and then 2x times 1. Then I'm going to move on and do minus 3 times x and minus 3 times 1. And in essence, I have actually just done FOIL because first means this one times this one, which is what I did first. Outside is this one times that one, which is what I did. Inside is this one times this one, and then last is this one times this one. So FOIL is really just telling you to be systematic. Start with the first term, distribute it through, move on to the next term, distribute it through. And if you learn it that way, then when you move on to this example, you're doing the exact same thing because you take the first term, the x, distribute it through. X cubed plus 5x squared minus 2x. Then move on to the second term, distribute it through. 2x squared plus 10x minus 4. And then you combine like terms. And it's none of this, ooh, when do I FOIL and when do I not FOIL? Just stop FOILing. Just always be systematic. Take the first term, bring it all the way through. Take the second term, distribute it all the way through. Okay, this one, it's a perfect triple, right? You have the same thing times the same thing times the same thing. If you have Pascal's triangle memorized, then there are shortcuts for these types of things. And anytime you have just a binomial, right? A two-piece thing, a two-piece polynomial raised to a power. Pascal's triangle gives us a fast way of doing them. But if you don't want to memorize Pascal's triangle, then forget it. Just write this thing out. You got 3 of them. Take the first one and multiply it through with the second one. Ignore the third one, right? So, distribute, distribute, distribute. You're basically FOILing. Combine all those like terms, put it all together, and then take the third one and do the same thing. Distribute it through with whichever's left. And if it's to the power of 5, you can just do that over and over and over again until you get your final answer. Yes, it takes more time than if you have Pascal's triangle memorized, but who really needs to memorize more stuff, right? So the idea of distributing through will work for all of these, no matter how big they are. So you can see what I'm talking about in action. I'm going to go through these kind of quickly because we just talked about them, but if you need to, just pause the video and look at them. All right, so here's our next one. Here's the last one. Again, see, doing what I'm doing, definition of a cube, just write them all out. Take one and distribute it through, and then once you're done with those two, then take the last one and distribute it through. Obviously, you want to clean it up first, which is what we did here, right? And then that's what we get at the very end. All right, so here are the shortcuts. I mentioned one already with Pascal's triangle. There's the FOIL thing. I'm just going to blow through this because I don't like FOIL. Do it the way I said. Just take the first one and distribute it all the way through. It's much cleaner. You don't need to learn FOIL. FOIL does not save you any time whatsoever. However, if you can learn patterns for powers, this can absolutely save you a lot of time. Now, if you don't, you just write it all out, like we did before. But if you can use Pascal's triangle because there is a pattern, right? If you started doing these, you would start to see the pattern, and that's what Pascal's triangle is that it came up with this pattern. And here's the first part of the triangle. And if you Google Pascal's triangle, you'll get these pictures again. But basically, this is what's happening with Pascal's triangle. And it's all how many powers do you have as to which row you go to. And then that tells you how many, what the coefficients are, right? So if we had something times itself, so x plus y times x plus y, then we would use this column, right? Because that's power of 2. And we would know that we would get a 1, a 2, and a 1 for the coefficients in front of those terms. If we had something raised to a power of 3, so x plus y times x plus y times x plus y, we know the coefficients are going to be 1, 3, 3, and 1. But remember, that's only if the two terms don't already have coefficients. If the two terms have coefficients, then those things are all raised to powers, and everything gets muddy. And basically, there is a more kind of generalized thing that's the binomial theorem. And it tells us how to figure out the actual coefficient. And here it is. So a plus b to the n, we're going to get n choose 0 times a to the n. Then we're going to get n choose 1, a to the n minus 1 times b, then n choose 2, a to the n minus 2 b to the squared. And you can see that the powers of a are going down by 1. The powers of b are going up by 1. There's b to the 0, then b to the 1, then b squared, and so on and so forth. So this number on the bottom is always the power of b, and then a is always n minus that number until you get to the very end. And this whole n choose n and n choose n minus 1, that's the number in the nth row r diagonal of Pascal's triangle. So if we're going n 2, then it would be the nth row and then the rth diagonal. I think it's a lot easier if you just learn how to do combinations and permutations, and then you know what a 7 choose 2 is. But again, Pascal's triangle, very limited. You only use it when you have something perfect raised to a power. So don't really bother wasting a lot of brain energy trying to memorize it. You can always just write these things out and kind of do them with brute force the long way. You're very rarely ever going to have something that's going to be raised to anything higher than the 4th power. So it's not like you have to do one of these to like the 15th power that would take all day without Pascal's triangle. So unless you're going to become a professional scientist, right, or a professional mathematician, there's really no reason to spend a lot of time learning Pascal's triangle. Just do it the old-fashioned way. Okay, another way to think about polynomials is to look at areas. We know that area of a square is s squared, area of a rectangle is length times width. So we can oftentimes represent the area of squares and rectangles by trinomials. And if we think of this basic trinomial, x squared, 3x, and 2, we can look at each of those terms and go, well, here's an area of x by x. Here's an area of x by 1, x by 1, x by 1. So there's 3x, right? If you put them all together, it'd be x by 3. And then 1 by 1 and 1 by 1, you put that together, that's 2 by 1. That's an area of 2. Okay, now if you take those bits and pieces and arrange them in certain ways, you can see that this length here is x plus 1, right? Because this was x, and remember this was 1 by x. This length here is x by 1, 2, so there's x plus 2. So x plus 2 times x plus 1, if you actually multiply that out, you will get x squared plus 3x plus 2. And that's one way to help you factor, right? That would be a really horrible way to try and factor these things. But you can kind of see, I guess, visually why this is true, why those two things are in fact equal. Here's another example, x plus 3 times x plus 2. Well, here's the picture of x plus 3, and then here's x plus 1, and we can see that this is what we get. Sorry, I just noticed a typo in the slide. This should be x plus 3 times x plus 1 and x plus 3 times x plus 1. Now it matches the picture. Here's x plus 3, here's x plus 1. And if you multiply these two pieces together, you get x squared plus 4x plus 3. But if you didn't know that and you kind of just drew the picture, there's my x squared, there's my 4x's, there's my 3 singles. Now, if you did it, with just FOIL, you'd get the same thing. If you did it with the picture, you get the same thing. Obviously, nobody's going to draw these silly pictures and figure it out that way. It's really just to remind you that, this stuff isn't just made up. It really does matter, and it really does work. But remember, don't waste time with Pascal's triangle, and don't waste time with foiling. It's better just to be systematic. Take the first term, multiply it through, take the second term, multiply it through, and that would be your polynomial. That's it.